Hey everyone, my name is Stefan. I'm a professor at University of Massachusetts, Amherst, and I'm also part of the Center for Quantum Networks, which is a big NSF engineering research center, one of those hopefully 10-year programs with a singular engineering goal. The center is pretty big. It includes SCORE partners, Amherst, Arizona, and a number of other institutions. It's really hosted at the University of Arizona, where a lot of quantum networking hardware is being developed, together with a test bed being developed in the Boston area. And a lot of the topics I will be presenting today are focused on the virtual test bed we're developing for the center, which to a great extent is used to try to inform, predict potential bottlenecks, what in the hardware needs to be focused on. That's on the low-level hardware side of things. And also it's a tool that today can be used by a lot of the CS folks that don't necessarily care much about hardware, but they're really interested in designing networking protocols for a potential future quantum network, and without having to worry about boring details like how do you actually build NV center-based repeater and so on. So with that, I also want to mention that the center has started a mini grants program where we're funding development on bug bounties, summer of code style projects. The goal is sure to help building out the software, but also to build out a community and to teach junior developers how to not just do good math, which probably they have already learned in their grad program, but also how to properly contribute to open source, how to do a Git pull request and so on. So if you're timid about that type of skills in your toolset, don't hesitate to start contributing. We're committed to helping building a next generation of competent collaborative programmers. So with all of that out of the way, I'll start talking about the stack that's being developed by the Center for Quantum Networks, and then focus on the software tool I mentioned. And then I'll specifically discuss some of the networking protocol development APIs we're building. So in terms of what you need to build a full quantum technology stack, you obviously need materials which exhibit some interesting quantum properties on a scale that's engineeringly useful. On top of that, you need some form of analog control, for which you probably should be using Piccolo. On top of that, now that you have some form of some form of analog control, you want to start pretending that you have a digital system so that you can start building scalable machines. Well, those noisy digital circuits that a tool like Piccolo can generate then need to be built into actual error correcting codes and whole error correcting schemes. And we also had presentations today on that type of technologies. And finally, when you have all of this, you can start talking about applications and algorithms, or in the context of the Center for Quantum Networks, it would be more network protocols and applications in terms of networking, communication, and sensing, not necessarily just computation. And to help with some of the design work on our end, we've started building a full stack design and optimization tool. The requirements we have for the tool are quite diverse. So we do need some form of symbolic description for quantum logic, and that and a number of other components were discussed at the previous JuliaCon, actually. So we already have a very humble, small symbolic core that lets us express algorithms and protocols in a backend independent way. Similarly, we are building a declarative noise model database so that you don't require everyone to submit a gigantic super operator just to model their error processes. All of this is meant to be translated to diverse set of backend simulators. So while the front end is symbolic, the majority of operations, the majority of the simulation happens numerically. And for some situations, we want to be able to model gigantic error-correcting codes over thousands of qubits, or purification circuits over many thousands of bell pairs. And for a situation like that, we'll be using a Clifford simulator. So all of the symbolics will be translated to a Clifford backend. For other situations where we are focused more on analog noise, we'll be using wave function simulators. And we're building also conversion utilities between those two if someone wants to work in the same situation with some low-level control that's then used for some large-scale purification network. Because a lot of this is focusing specifically on networking, we naturally need a discrete event scheduler, which has been a frustration because in Julia or really any other language, those are fairly immature tools. That's probably also some interesting sociology questions here. Why is this type of tooling not as mature as many other libraries we have available? And a goal here is also to make this very Lego-like, so that a network scientist can use it without having to worry about low-level hardware and vice versa. So, with all of this out of the way, the software tool is called QuantumSavory, more or less a joke on the SPICE classical electronics simulators, also the best SPICE you can get in the Balkans. And I want to focus on what we're doing in order to make network protocols composable. I want to spend a minute to defend the idea that we're even caring about quantum networking. The application is not as immediately obvious necessarily as quantum computing, so I want to just to set the stage for that. So imagine Alice has a qubit, Bob has one too. Those qubits can be correlated, and then they can be correlated in ways that are not possible classically. If you list the possible correlated states for a classical system, you won't span such a basis of 4 different states. You have much more richness in terms of available correlation in the quantum case. And I won't go in detail through this, given the audience, that's probably fairly obvious. But a few years ago, I participated in setting up an art installation that explores these ideas. It was a fun setup that I encourage you to look up. It was at the Yale Quantum Institute. You were basically walking through a large dilution refrigerator, and depending on your location, you were making non-commutative projective measurement, and it was a way to teach the public about non-commutativity and hidden variable theories. But what can we use these non-classical correlations for? So one of the obvious hyped up applications is in security with quantum key distributions, but there are much more interesting ones as well. This type of correlation provides you with a trade-off between bandwidth and space. Basically, in advance, you can store in memory bandwidth that you can then use when the network is congested. Something not available classically. The quantum primitive to use here would be something called superdense coding. Similarly, you have new types of sensing here that can go beyond classical limits, again, thanks to the sacrifice of entanglement. There is the more mundane application where you're networking existing quantum computers. And sure, maybe that won't necessarily be interesting when you're talking about large-scale networks, but modular hardware in the same fridge will need its own networking protocol as well. And lastly, one of the main reasons we should care for this scientist is that nature really doesn't like this type of object existing. And if you're able to create something that's so unnatural, you probably will be building technology that's applicable in many other domains as well. The finesse necessary to build this type of states does translate into better technologies in plenty of classical applications. So let's go through a case study of a typical networking problem in which if you use most of the available tools, you will start having a lot of frustrations when you're trying to build something large and composable. Let's focus on the need for repeaters, the repeater chains on a large network link. So in fiber, you have, or really any other media through which you'll be transmitting a qubit, an optical qubit, you have exponential loss. And that exponential loss puts very hard limits on how long a link can be if you want reasonable fidelity or reasonable rate for the established entanglement. So a typical solution in such a setting is to set up repeaters in which you perform some form of, let's call it, entanglement swaps. So in this animation here, we have, let's see, 5 repeaters. Every repeater has 2 slots. And all that these repeaters are capable of is establishing entanglement links between neighbors. You cannot establish a link from here to here. The loss at such a long distance will be just too prohibitive. On the other hand, you can in parallel establish links between neighbors. Those are much shorter links, so the loss is by far not as damaging. And there is an operation in which, called an entanglement swap, in which locally you interact with your 2 halves of 2 different bell pairs, and that extends those 2 bell pairs into 1 long bell pair. This is the entanglement swap protocol. Here you can see that frequently here we have 2 bell pairs in this direction and in this direction, and the swap basically makes them span this whole gap. And you'll be doing this at each register until you have a long-range entanglement that you will be consuming, and in this particular simulation we have a plot of latency versus quality of entanglement for the whole link. So how do you actually program this? How do you model this in a real network? In our setup, the goal is to make it as simple as possible. It's nothing more than setting a couple of different networking protocols that somehow work together in a composable way. And discussing how to make it composable is my main goal here. But just to showcase the simplicity, we just run the start of a process, of an entangling process between on each edge of the network. And then we start a swapper process at each node, and an entanglement tracker process that tracks the metadata necessary for these basically classical communication protocols that govern the quantum network, also at each node. And it's not an exaggeration that pretty much this is all you need to create a plot like this in our simulation tool. So design considerations that we're facing here is that we need something that lets us track all the classical messages between these quantum nodes in a way that's scalable, in a way that doesn't require a bespoke code every single time you add some new networking dynamics. And in particular, these 2 protocols that are running on each node, they need to communicate with each other. How do we set up this communication so that we are not overwhelming the developer with special cases? Well, let's run through an example of this protocol in the abstract. We have Alice and Bob, which are the end nodes, and we have a repeater in between them. The repeater will establish a link with Alice and a link with Bob. And some classical controller will then know locally that Alice will know that she's entangled to the repeater will know that they're entangled in one way to Alice, in another way to Bob, and Bob will know that they're entangled to the repeater. The repeater then will detect that they now have an opportunity for a swap. They have 2 halves of a bell pair, 2 different bell pairs in 2 different directions. They'll perform the swap, but then they will need to tell Alice that, hey, Alice, you're not entangled to me anymore. You're actually entangled to Bob. And the difficulty is tracking this type of messages when you really want to build a large network that's not necessarily one-dimensional. Even in the one-dimensional case, if you have a chain of repeaters, it starts getting pretty annoying because Sure, repeater 1 is entangled with Alice and repeater 2. They perform a swap. They tell Alice. They also tell repeater 2, but by then repeater 2 also had performed the swap, and repeater 2 is not entangled to repeater 1 anymore. The repeater 1 and Bob are the ones that were entangled after this swap at repeater 2. So messages will need to be propagated through the network as well. And you will need rules for that, different protocols for that. And most annoyingly, you would want those protocols to work even if you are running a ton of other processes that might be congesting the network or fighting for resources. So what do we need from such an API? We need some metadata for describing each node's local knowledge of what the network as a whole looks like. The node's belief about what their entangled state is, and anything else about the state. It doesn't need to be just the question of entanglement. We need some way for nodes to be querying this local metadata, to search through it, to decide whether they're at a stage at which they can perform something interesting, like, for instance, a swap. We, of course, want to have visualization tools for that metadata. And most importantly, we want composability of these protocols and of this API as a whole. And again, when I was talking about these protocols, I mentioned a couple of times, it won't be just swaps. This was one example. But at the same time, you might be running super dense coding between two nodes of the network. You might be running teleportation of logical qubits on top of which you're running some form of error correction, beneath which you're running some form of entanglement distillation. The entanglement distillation will be fighting for resources with the swaps. The swaps and the distillation will need to be scheduled with respect to each other. There will be a lot of frustration in sharing of resources here. And the state of the art in the existing tools is kind of, if you compare to the classical internet, where every single protocol, every single application protocol, like Skype and Zoom and web, had to have its own packet type in the networking layer. There is truly no separation between application layer and networking layer in the current simulation tools. And you cannot track resource congestions in a viable way with current simulation tools. We believe that we have the first steps to a reasonable solution here, basically a way to track metadata where you don't need to hand-stitch every single protocol, where you don't need to make bespoke changes to protocol A if you want to implement protocol B, which is the current state of the art, basically. We want to have the composability that Julia enables in many other domains. So we're setting up a pretty simple tag and query API. So in the next few minutes, I'll just run through an example of how this API is used to implement the aforementioned protocols in a more composable way without having to explicitly create links between the protocol processes. So we'll be able to record some form of metadata. For instance, in the entanglement protocol, we'll be tagging. This is the protocol that creates the initial row bell pairs between nearest neighbors. We'll be tagging locally the slots that are entangled with some form of metadata. Here, we've decided to call that metadata the entanglement counterpart struct with some fields that describe exactly who you're entangled with. What is the other node you're entangled with, and on that node, which specific qubit register are you entangled with. There's a couple of simple add-ons here in terms of pretty printing and pretty visualizations, where Mackie immediately gives you that metadata when you hover over the qubit. You can see that this particular qubit, the classical metadata describing this qubit, that's stored completely separately from the quantum state, does tell me, the controller of this local node, that I have a belief that this qubit is entangled to some other node. We also will need a couple of other tags, like we'll need the entanglement history tag. If a swap happens, the node will not have entangled qubits anymore, but the node will need to retain knowledge that there were entangled qubits here that I swapped, because later down the line, the node might receive a message, hey, I did something with my half of the entangled qubit. And you will need to propagate that message. And that's a particular example for swaps, but it scales to other types of protocols as well. Similarly, if a swap is performed locally, I will need to send to the remote nodes an entanglement update message. Again, the names are arbitrary, but roughly the type of metadata you need to store semantically would be the content of where the swap happened and how you need to update your remote belief about who you're entangled to. Well, that's for storing the metadata. Then the more important part is really querying the metadata. For instance, the entanglement tracker would be one of the controllers that updates the metadata when they receive messages from remote nodes telling them that, hey, I've performed a swap, you're now entangled to someone else, not to me. So the entanglement tracker will need to query locally for entanglement history data, and importantly, the query needs to be capable of wildcards. So you can put these emoji question marks in the query function so that you can find all tags that map the query up to a wildcard. So here, these are specific values that you need to be exactly equal to in your query. But these are values that can have any value. And similarly, you also have access to predicates. For instance, here, this would be in the swapper protocol deciding whether to perform a swap. And they will be checking whether they have two entangled qubits here. This is checked for one of the entanglement components. And there might be a predicate for, hey, check whether the coordinate of the node I am entangled to is to the left of me, thus ensuring that there's some directionality to the repeater. Again, we have access to wildcards, and we have access to other metadata about the qubits, whether they're locked by other processes, whether they're assigned, and so on. The details don't matter too much. The overall idea of tagging and querying, though, is what permits the composability here. And this enables much more sophisticated protocols as well. So I'll run through one or two pretty examples, and then I'll open up for questions. For instance, here's an example of a quantum switch. The way we define it in this context is that we have some star network where we have a center switch, and we have many clients. And a client wants to be entangled to another client. They'll make a request to the switch to, hey, please entangle me to this other client. But all the network is capable of is creating entanglement between the clients and the switch. The switch will need to perform one of those aforementioned swaps. Here, again, we have a set of tags, of packets that announce, hey, I'm requesting this resource from you. The switch is querying what the currently received packets. The switch is also querying what is the current state of entanglement that's available to it. It performs some interesting graph optimization problem internally, and then it sends out tags saying, yes, I'm attempting this type of communication. You'll be the first to fulfill your request. And the simulation tracks the backlog of requests and so on. You can change the request rate between every single pair. If you globally change the request rate to be very low, you see how this is a plot of the backlog over time. The backlog starts dropping. So it lets network scientists compose many protocols and study their performance on real models of hardware without having to learn anything about the low-level models, and without having to write bespoke protocols for every single simulation. Okay. Yeah, and again, the simulation overall is just a set of processes that make requests between each pair, a set of processes that track entanglement at each node, and one process, the entanglement switch in the central node. Of course, the switch process itself is pretty complicated internally. It has a ton of optimization routines in order to decide which link to be fulfilled first. But in terms of communicating with other protocols, it just uses one or two queries, and it just uses one or two tagging functions. This is another example of repeaters, this time on a grid, where we want to connect this node here and this node here. But again, we have only direct links between nearest nodes. And this simulation runs with exact wave function simulation, although we have many hundreds of qubits. Because the entangled pairs are never more than 4 qubits, we don't need to worry about scalability. All of the nodes have concurrent processes running on them, and the entire simulation was, again, this whole thing was generated in maybe 10, 20 lines of code, because we have these visualization tools and because we have these composable protocols. Sure, the code to create the protocol is not necessarily trivial, because there's some protocol logic to worry about. But as I mentioned, the protocols are composable because their communication with the other protocols are nothing more than a couple of queries and a couple of tags. And with that, I'll be closing. I want to mention again that we're running, since last week, a lot of bounties, both large-scale Summer of Code style projects for more advanced developers, and small bounties for people that want to have their first taste of open source development. We're also hiring contractors for a lot of this work, including potentially part-time, remote, worldwide. And on the more academic side of things, we're hiring both graduate students and postdocs. So message me if you're interested. Amherst is very pretty and bucolic. And that's all I have.
Any questions?
Yeah, thanks. Very interesting talk. I have a high-level question, maybe. So if I'm thinking about routing and standard network protocols, right? There's of course tons of algorithms out there, but they make certain assumptions about the network, and I can definitely see these assumptions not satisfied in your setting. Like, you know, especially when I think about noise and potential noise correction and so on and so forth. So, I mean, you showed this example with a switch, but now scaling this up a bit, have you thought about the sort of the underlying optimization problem, the routing problem? Is there something that's in your head, and you can say a few things about that?
So I would say that's a type of research program that problem that people in the CQN want to solve. Some of them purely theoretically, some of them with a tool like this. The current workflow in the center is usually, you have a lot of classical networking folks that have some extremely abstract definition of a network, maybe large, maybe small, and they solve something within their context. They make proofs about stability of the network, proofs about scalability, proofs about amount of overhead for some type of communication or congestion or whatever. And then they go to the CQN Summit, they present that, and the experimentalists don't engage with it because to them this is so incredibly unrealistic. A tool like this, the goal is really to make it possible for these theoretical proofs to easily be then turned into a simulation that can be verified in a way that's informative for the experimentalists, that do take into account much more about the hardware. So here I'm describing the use of this tool more as a way to vet a theoretical protocol. In the opposite direction, I think, is more closely to what you asked. You implement the protocol and you're running some form of optimization. This is much more nascent in terms of what we have here, but we are already working on tools related to stochastic AD so that we can do some form of gradient descent over the stochastic processes that are running on the network. But that's right now pretty experimental, not really part of the bigger software as a whole. And then there are all the more naive ways to do optimizations. The tool is scalable because of the modeling techniques we have put in. So you can do the naive thing of running a few thousand simulations and just varying parameters. It's just that, sure, it works, but it's not something to brag about.
Any more questions? Okay, if you no more questions, let's next step.
I could ask one question. I don't know if you could speak to like what the current state of like the hardware infrastructure is. Like at, I know Chicago has some, and you mentioned Arizona. So I don't know. I'm not up to date on where we're at, but I know distances are getting bigger and stuff like this.
Very quickly, because I imagine I'm running out of time. The Boston test bed is meant to be technology demonstrator over long range. So there is. Lincoln Lab, MIT, and Harvard are connected together with a single fiber that's occasionally in bad condition. But now they are demonstrating various forms of entanglement distributed over these, I think, tens of kilometers of links. Then the Arizona is a campus-wide network. It's a much smaller network, but it's meant to be a system integration hub where you're not demonstrating long ranges, but you're demonstrating that you can actually build 20 nodes together, even if they're closer. So it's much more about the engineering difficulties of building a real system. So yeah, you probably know the term integration hell.
Okay, let's thank Stefan, and we'll have a short break.